Hi guys, today we're gonna talk about vectors and cover them. To cover them, we need to know about vectors descriptions, vectors identities, operators that we use about vectors, and some definitions for vectors. At first we have to define a vector. For definition of vector, we have two ways to do it. The first definition is advanced definition of vector in the advanced mathematics, but we don't need it in our calculations, and we use the second definition that is more simple and easy to understand. But anyway, the first definition is a vector is an element of a vector space. The reason that we name it vector space is because it really works like a space. Would define something like a space. The vectors are inside it. That vector space include vectors. For example, a sum A as a vector space, it's something like a set that its members are A, B, and other vectors. But we can't say any set vector space because they have some conditions to be vector set. Something like this, that if A is inside A vector space, and also B same as A as in A vector space, we should have A plus B and A2, and some conditions like this. But some definition that we need is this definition. It's more simple, that vector is only something that has magnitude and direction. With these two identities, we can name something vector. And how we show them? To show vector, just we draw something like arrow and its symbol, its name. For example, it's v vector. And the magnitude of a vector, we show it as this one. Something like absolute value of a number that we used. And it's about vectors, it's the magnitude of vector. And about direction of vectors, we use this symbol. It's for itself a vector with magnitude 1, but the direction is the direction of v. And also this one is a scalar value that you know. For example, it's 1 or 2 or any number that you think. It's direction of v that was shown it as v hat. So if we want to start, we show vectors graphically with an arrow. For example, is v vector. This tiny hat at the end of the arrow shows direction, and also the length of the arrow shows magnitude of a vector. So it's a way that we show vectors graphically. And as I said, that we can show magnitude and direction like this. So we can show a vector, any vector like this. The magnitude of vector times its direction. It's v vector. So let's define some operators and work with vectors. So some operators that we use is, the first one is sum operation. So to use sum operation, we need to calculate a plus b. We can define it graphically now, and then we'll write it algebraic. Sm, this one is a vector, and this one is b vector. I would like to say this vector as a plus b. Actually, it's our definition for a plus operator. Just this. So to like vectors algebraic, because working with vectors just graphically is really hard. And there is sometimes that we need to work with many vectors and many difficult equations that we can't really do them graphically. So we need a way to work with them with a system like algebra that is simple and it's with equations, not a graphical figure. So to do this, we define coordinates. Most simple coordinates that we can define is Cartesian coordination. And this one is x-axis and y-axis. It's two-dimensional Cartesian coordinates. We can use vectors in any direction, any dimensions, even more than 3 dimensions. So in this coordinates, we can draw vectors like this. It's a vector and it's b vector. As I said, the two identities that determines a vector is only magnitude and direction. So the place of vector in our coordinates doesn't matter. So we are able to move vectors in xy plane or in our coordinates without any problem and any change. So to sum to a and b vector, I prefer to move b here to be able to use this graphical definition. As I said, this one is a plus b vector. So at first we can write vectors as sum of scalars and some directions. I mean, we can break down a vector to its magnitude and its direction, as I wrote here. And with that graphical definition of sum of two vector, you know that I can write a vector, sum of these two vectors, ax and ay. So a vector is equal to ax plus ay. And we don't like usually to set them a vector. I mean, why should I break down a vector to another vectors? So I prefer to break down them to scalars and directions. As you see in figure, AX direction is parallel to x-axis. So it's AX is scalar, it's a scalar, x hat. And AY is AY magnitude, or I won't write the magnitude because it's scalar by itself. And it's y hat. So we can write a vector as ax x hat plus ay y hat, and these are scalar, and these are vectors with magnitude 1. So we can do them for b and a plus b and any vector. So let's determine a plus b like this, with some scalars. So this one is ax, and as I said, now it's not vector, it's a length of it, and we'll know it as a scalar, and it's the magnitude of the vector that you know. So this one is bx, this one is by. So if you want to describe a plus b with this one, if you say, you can write its x-axis like this: a plus b is equal to its x-axis as ax plus bx. Here bx is negative because it's an opposite direction of x-axis. I mean, this vector is going to decrease x-axis. So this is x of a plus b vector, and it's ax plus bx, and it's something like this. So for its x-axis, it's ax plus bx in direction of x hat, and as well as x-axis, we can write it about y-axis. It's ay plus by. So it's ay plus by in direction of y hat. So it's a plus b vector, and we'll show this with this way. And it's a plus b with vector 4. So we've covered sum operator. Now we're gonna talk about multiplication of vectors. There are too many ways to multiplicate vectors, and the first one is this: multiplication. The first one is a scalar times a vector. Here n is a scalar and v is vector. So how we calculate this? We have to define this at first. So the simplest definition of it is this: assume that it is v vector. So and Scalar will only multiplicate it in this vector's magnitude. I mean, if it be v vector and n equals to 2, I mean we're going to draw 2v. The direction won't change, but its magnitude will be multiplied by that scalar thing that we multiplied. So for 2v it will be like this, that its length is 2 times of v. So it's the multiplication of scalar by vector. But about two vectors to each other, we can do something. At first, you can do something with scalar multiplication. Sm(n) is scalar again, and you want multiplicate it and sum of two vector. So it will be n times ax x hat plus ay y hat plus bx x hat plus by y hat. So you can write this completely as a vector. If you see in figure, when its length is going to be multiplied in a number, the x-axis and y-axis would change, and it will be multiplied in this number too. For example, assume that it's a v vector with vx and vy. So if this one, this bigger one, be nv, it will be what? Assume that it's theta, so vy is magnitude of v sine theta, and vx is equal to magnitude of v cosine theta. And this one about nv, it's vy prime and it's vx prime. Vy prime is magnitude of nv and sine of theta. And as I said, magnitude of nv is n times magnitude of v. I mean, it's n times magnitude of v sine theta, and vx prime is n magnitude of v cosine theta. And as you see, any of these axes are going to be multiplied in this number. So n times ax x hat plus ay y hat is equal to nax x hat plus nay y hat. Simply, it's like simple algebra, and we can multiplicate it in all sentences inside parentheses. So we were here. We were going to calculate this one. I mean, we had to calculate n scalar times ax plus bx x hat plus ay plus by y hat. So it will be like this. If we use it, we have n times n ax x hat plus n bx x hat plus n ay y hat plus n a n by y hat, and it's equal to na plus nb. So you can write n times a plus b as na plus nb. And it was about scalar multiplication. To multiplicate two vectors to each other, we have two definitions. To multiplicate a vector and a vector, you have two ways. The first one is dot product. The dot product between two vectors will be written like this. It's a dot b, and its graphical definition is this: if it be a vector and this one be b vector and this one theta be the angle between them, a dot b is defined magnitude of a, magnitude of b, cosine of theta. It's the definition of dot product. Its graphical scene is we will calculate this length, that is b cosine theta, and multiplicate it in all length of a. Or we can do it reverse. I mean, we can calculate this one length, it's a cosine theta, and multiplicate it in all b length. So we can write them like this. But we can prove something about dot product in Cartesian coordinates, and it's this. Assume this Cartesian coordinates x-axis and y-axis. Here we have a vector and b vector. And this one was theta. Assume that this angle is beta and this angle is alpha. And I said it's theta. So theta is beta minus alpha. A that's b, that is a scalar thing, as you see it here. It's a scalar. A dot b is A, assume it as magnitude of A. B, cosine of theta. So we can write theta as beta minus alpha. I mean cosine theta is equal to cosine beta minus alpha, and it's equal to cosine beta cosine alpha minus sine beta and sine negative alpha, that it will be plus sine alpha. So you can write it, and A that's B is equal to A B times cosine beta cosine alpha plus sine beta sine alpha. Here all of these variables are scalar, so we have simple algebra. It's equal to AB A cosine alpha B cosine beta plus A sine alpha times B sine beta. And if you see, this one is AX, it's BX, it's AY, and it's BY. So in Cartesian coordinate, we can write A that's B, AX, BX, plus AY, BY. And these are the length of vectors and say axis. And about this kind of multiplication, if we dot a vector and some of another vectors, for example A dot B plus C, you can write B plus C as vectors and different coordinate in Cartesian. It's B x x hat plus by y hat plus cx x hat plus cy y hat. So as we said, you can write A also like this, and you can use this method to calculate dot product, and it will give you A dot B plus C as AX x hat plus AY y hat dot BX x hat plus BY y hat plus CX x hat plus CY y hat. And if you use that method that I've said, you can write it as AX times BX plus CX plus AY times BY plus CY. And it's AX BX plus ax 6 plus ay by plus ay cy. These two sentences are a dot c, and these two sentences are a dot b. So we can write a dot b plus c as a dot b plus a dot c. In dot product. Another multiplication method is cross product. This one is something like it. It will be defined with this method. As some three-dimensional space will write. I'll drawing Cartesian coordinate with three dimension. That it's x, it's y, and it's z. Sm, it's a vector in xy plane, and this one is b vector again in xy plane. We define a cross b vector as a vector here. It's a cross b. And it's vertical to another two vectors. I mean, a cross b is equal to is vertical to a and b. So you can find a direction of a cross b with right hand method. To do that, assume it's a vector and it's b vector, and you wanna determine the direction of a cross b. So put your hand and your fingers straight on a vector, if the first vector of operation, that here is a. So your fingers should be on this vector. Then try to your hand should be vertical to plane. I said. Then try to close your hand and find direction of your hand. In which direction should you put your hand to? With closing your hand, your finger will be closer to B. I mean, to close your fingers to B, you should move your fingers in this direction. Then to do it, you should put your hands in a way that your thumb be out of a screen. I mean, your thumb should be toward your face, and your thumb will show the direction of A cross B, that here's an out of screen toward your face. So B cross A is negative A cross B. With this method you can understand it, because you will change your hand direction to do this. And we have two things simple to show vectors that they are not in the plane that we are drawing on paper. if you saw this symbol, it's a vector that is its direction is toward your face, is coming out of the screen. But if you saw this symbol, it's showing direction of a vector that is going inside of monitor in your display. It means that it's going to be farther than you. So with this way you can show vectors that are not in plane that you're watching. But something else about cross product is this, that we will prove in another video. You can do it by yourself and try to prove it, and you will see the answer and its proof in next video. You can write A cross B in Cartesian coordinates as determinant of this matrix: AX, AY, AZ, BX, BY, BZ. Determinant of this matrix. But if you don't know matrix, don't worry, because we'll cover it in another video. But to do this, you can prove that A cross B is equal to AYBZ minus AZBY X hat minus AX BZ minus AZBX Y hat plus AXBY minus AYBX Z hat. You can prove this for be sure that you can work with vectors, or for a practice, and we'll prove it in next video. So something that we learned in this video are this. At first we told definition of vector, then we define a vector, define a symbol to show a vector magnitude and a vector direction, and we define some operator for vectors, and we showed it graphically. Then we break down a vector to some scalar and direction and Cartesian coordinate. And then we got into multiplication. We have learned about multiplication of scalar and a vector and its identities and a description of it and something about it. And then we got dot product of two vectors, and we prove that in Cartesian coordinates you can write it as this. And finally we'll learn about cross product for multiplication between two vector. We define it, we show you how to determine its direction, and finally there is a way to write it in Cartesian coordinates that we will prove it in next video. Thanks for watching video. please subscribe us, and thanks for watching.